So just going to talk a little bit more about the method of initial rates, show another example so that you can see just a little variability. So in general, right, so the rate law is the rate constant K, which is determined after doing a series of experiments. It's the change in concentration of whatever the first reactant is to some power. And then if you have a second reactant, to some power if you have other reactants. To their power. If M or N, usually most reactions are one or two reactants though, but if M or N are equal to 0, then the concentration of that reactant has no effect on rate. If you have M or N is equal to 1 and you double the concentration, then you're going to double the rate. If you get a second order, there's 2 exponent there, but if you double the concentration, then you're going to quadruple the rate because 2 to the second power would be 4. And if M or N is equal to 3, then if you double the concentration, you're going to increase the rate 8-fold. So obviously the higher the exponent, the more that reactant affects the rate of reaction. And so you can just kind of see those are the common ones for trends. So let's do another one, different reaction here. We've got ammonium ion with a nitrite ion making nitrogen gas and water set at a certain temperature. They ran a couple experiments and to collect data of the change in concentration initially, at initial time, and the initial rate. So we're going to determine the rate law. All right, so what we want to know, so rate is some constant K. And for this reaction, it's going to be the change in concentration of the ammonium ions raised to some power, which we have to determine, and then the change in concentration of the nitrate ion raised to a different power. So you usually just start with the first 2 and see what changes. So we've got experiment 1, 2, and 3. From experiment 1 to 2, we're decreasing the concentration, cutting it in half, but this one is remaining the same. So we can actually look at and determine how the ammonium ion affects the rate. So let's set that up. I'm going to do experiment 1 to 2. I'm going to put the higher one on top. Last one I did 2 to 1, doesn't matter. You can get it either way. It's just usually easier if you put the higher concentration on the top. So experiment 1 rate to experiment 2 rate is going to be the change in concentration of the ammonium ions. For experiment, we're looking to find this M, but so this is for the first one over the change in concentration for the second one, so some power. Anyway, so let's plug in the actual values here. We have, so experiment 1 is 7.2 times 10 to the negative 6 units molarity per second over the 3.6 times 10 to the negative 6 molar change in concentration per second is going to be equal to 0.24 molar over 0.12 molar. Those units will cancel, but it's raised to some power m. That's what we're trying to solve. So what we end up getting here is we have 2. Okay, if you divide those, you're going to get 2 is equal to 2 raised to some power. So that means that m is equal to 1. So we determined that the m is 1 there. The concentration if you double the concentration of the ammonium, you're going to double the rate. If we look at 2 different experiments, so here from 2 to 3, this one's staying the same, and this one is increasing by like 1.5 times. Let's see what happens to the rate here if we would do the math. So this time I'm going to put well, I'll just show you if I put like the lower value on top. You can still solve for it. Okay, so I'm going to do experiment 2. You can flip it and do experiment 3 to 2. I'm going to do experiment 2 to 3, and that's going to be the rate. So the rate at experiment 2 is the 3.6 times 10 to the negative 6 molarity per second over the 5.4 times 10 to the negative 6 change in concentration per unit time. And that's going to be equal to 0.10 molar over the 0.15 molar raised to some exponent n. And what you get when you divide these two is you get 0.67, so a decimal, and then you're going to get it's equal to 0.67 raised to the n. So in this case, n is equal to 1 as well. There. So in this case, the rate law then is rate is equal to, so both of them double the rate when you change the concentration. So K in ammonium ions raised to the 1, which is implied, and the nitrate raised to the 1, which is implied, which it does happen to match the coefficients, but that's just coincidence. So the next, usually then what you'll be asked to do is, well, determine the rate constant for the reaction with units. And so I'm going to pick the rate. I think I picked, okay, I'm going to pick experiment 3. It doesn't matter which one. So I'm going to put in the 5.4 times 10 to the negative 6. That's the rate. 5.4 times 10 to the negative 6. I'll use the big M's this time. Molarity per second is equal to K. And then I have to put in the concentrations for experiment 3. So the ammonium is 0.12 molar. And the concentration of the nitrite ion is the 0.15 molar. So unit-wise here, you're going to get 5.4 times 10 to the negative 6 molarity per second is equal to K. And then when you multiply these two, you're going to get 0.018 molarity squared. And so K is then going to be the 5.4 times 10 to the negative 6 molarity per second over the 0.018 molarity squared. So you can also do it this way. And numerically, you're going to get 3.0 times 10 to the negative 4th. And then unit-wise, you've got this molarity will cancel, the square will cancel. So you have molarity in the denominator per second, that's K. Or if you then write the expanded version, you'll see that more common. You're going to have 3.0 times 10 to the negative 4th liters over moles per second. That's the rate constant for this one. So just another example there. And I guess I think I have another example, and I'll probably do another one in class just to show, you know, if you don't have just first orders, how to solve for it. But that just gives you another example, walking you through. Then the last thing that they could have you do is they could say, well, determine the rate if you have certain concentrations. So we now have, oh yeah, and this is another way that it could be written. So it could say like, okay, determine the rate. I mean, now that you have K, if the concentration of this is 0.50 molar and the concentration of this is 0.25 molar. So then it's just plugging it in. So you would have, okay, rate, and we can see then how the units cancel with this K. So we've got this 3.0 times 10 to the negative 4th. I will put the, yeah, let's just do molarity on the bottom per second. And then we're going to take our 0.50 molar and our 0.25 molar, and then you could calculate what would be the rate of reaction for this, because you can do it at any concentration. So for this one, we would get, but you can't determine the rate if you don't have the rate constant determined. So for this one, the rate would be 3.75 times 10 to the negative 5th, and then unit-wise, you can see here that the rate constant allows it so that the rate is in concentration per unit time. So it does depend on what the magnitudes of this. So 1 molarity will cancel, and then you still have change in concentration per unit time. And that would make sense since rate is a change in concentration per unit time. So those are the types of problems you can have. And yeah, ask if you have questions, but that's just another example for you.